Good morning, dear students, and from today I'm going to start a lecture series based on the topic complex analysis and integral transform. This is a topic covered by BTech third semester program. Myself, Dr. Kamarji, and today my first lecture. And under this topic, I will cover today introduction to the analytic function. That is the first topic in which introduction to analytic function. Actually, this is the first topic, analytic function. That is the first topic of the complex analysis. This is your first module. So before starting introduction of analytic function, first of all, you have to know what is the complex number, because here we studied about the calculus characteristic of the complex function. Complex function means a function of complex number. So first we discuss what is complex number. Already you have studied this at class 11, 12 level. Complex number. What is complex number? Actually, if we take an ordered pair of real number x, y, so this is a complex number. This ordered pair is called complex number. Mathematically, you know that it will represented by z equal to x plus iy. This is its Cartesian form. Here you know that x is a real part of complex number z, y is imaginary part of complex number z. This is the basic concept of complex number. It can be also represented into the polar form by putting x equal to r cos theta plus y equal to r sin theta. So this is r times cos theta plus sin theta. It can be also represented as r e to power I theta, because you know that by Euler's formula e to power I theta equal to cos theta plus I sin theta. If here we take x equal to r cos theta, y equal to r sin theta. If we squaring adding both, then we get z equal to x square plus y square. It is represented by mod z. This is the magnitude of the complex number, and if we divide this, then we get value of theta, that is tan inverse y by x. This is the argument of complex number, right? This is the basic concept of complex number. Here we also use z bar. Z bar means, you know that, conjugate of this complex number. Only we replace I by minus I, that becomes x minus y, that is z bar. And you know that if we add z plus z bar, we get 2 times of real part of z. If we subtract this, then we get 2iy, that is the imaginary part of complex number z. This is the basic concept. What is the complex number? Now, for introducing analytic function, we have to know what is the complex function. What is the complex function? Complex function, if we take a function of complex number, you know that function is denoted by this f of z. Then, as in complex number there is a real part and imaginary part, similarly here complex function having 2 parts, u plus iv. Here fz, because it is ordered pair, so this is function of 2 variable f of x y. U is also function of 2 variable, v is also function of 2 variable, and this is a complex function. This is a complex function. Here in this complex function, again there are 2 parts. One is real part, means u of x, y. This is a function of 2 variable, but here it is a real part of complex function fz. V of xy is imaginary part of complex function fz. So this is concept of complex function. Now here is one difference. If we take z as a single function, then this is single value function. But you know that z is an ordered pair of two real numbers. So if we see here fxy equal to u of xy plus I of vxy, so this is a function of two variables. Now for analytic function, we discuss all the calculus characteristic of this function. You know that what is the characteristic? Means we have to know what is the limit of complex function, what is the continuity of complex function, and what is the differentiability of complex function. Right? So first we discuss limit of complex function fz. Limit, you know that number L is limit of complex function fz at a point z equal to z naught. If limit z tending to z naught of fz equal to L, means if z is approaching to z naught is also complex number, then there exists a value which is called limit of this function. In differential calculus, when you take ordinary function, then you know that there also approaching value of a function is limit, and for the existence of limit, there you check what is the left hand limit and what is the right hand limit. When both limit exist separately and coinciding, then you say that limit of function exists, and that is the limiting value. But here, because this function of two variables, so concept of existence of limit is different here. Here we see that function is of two variables, so existence of limit depend upon this existence depend upon the various paths. If limit is independent, value of limit is independent of the different path, then we say that a limit of function exists. We will discuss later. Now, second thing, this is the first characteristic, the limit of function. Second thing, we have to see that what is the continuity of function. Continuity of function fz. Whether this function is continuous or not. How we check this? So continuity, you know that if limiting value of a function is equal to the value of function. If this is equal, limiting value is the left hand side, that is the limiting value at point z2, and this is the value of function where we have to check the continuity. If these are equal, then we say that fz is continuous at point z equal to z naught. And this is again function of two variables. So process to check whether function is continuous or not will be changed, and that will again depend on the existence of limit. Means we have to check the existence of limit on the left hand side. If this is independent of path or not. If this is independent of path, then we say that limit exists. If this value is equal to the value of function, then we say that function is continuous. And now third thing, that is the differentiability. Differentiability of function fz. This is the third characteristic of the function in calculus. What is differential function? Means if function is differentiable or not. Again, by definition, if fz is differentiable at a point z equal to z naught, if limit z tending to z naught of fz plus z naught minus value of function divided by z. If we take this limit z tending to z naught, f of z plus z naught minus fz z0, if this exists, if this limit exists, then function is differentiable. Limit exists. What is the meaning of existence of this limit? If we take this one, we say that limit z tending to z2, z naught z plus z naught minus f z naught upon z. If this limit exists, then we say that function is differentiable. And the value of this limit is denoted by f dash z naught. And it is called actually derivative of function fz at point z equal to z naught. Right? This is the third characteristic. Means if function is continuous, then it may be differentiable. Then by this process, because here again function of two variables, f of z plus z naught is a function of two variables, this is a function of two variables. The concept of existence of limit is again changed, because we have to check the value of limit is independent of path or not. If limit exists, value independent of path, we can take here various paths, because what are the paths? If you take xy plane, suppose xy plane we take, so there are a number of paths by along which we can take the value of limit. First path, you can take any general radius vector y equal to mx. Along this we can take the limit. Real axis, this is real axis. X-axis is real axis. Real axis means equation, you know that y equal to 0. This is, you know that imaginary axis, that means x equal to 0. So these are three standard paths. Some also path can be taken by the given value of the function in a particular path. So we can calculate the value of limit along those paths, along three of two paths or two of three paths. And if the limit is independent of path, then we say that limit exists. If limit of function exists, then we can go for the existence of continuity. What is the value of function? If this limit is equal to the value of function, then function is continuous. If function is continuous, then we can do further differentiability. Now we calculate this limit. If this limit exists, again, existence of it means that is the independent of path. Then function is differentiable. Now, this is your just introduction. By this introduction, you can say this is a foundation. What is the analytic function, and what is the different properties and characteristics of the analytic function? This is your main topic. From that topic, your this complex analysis and integral transform, your part of syllabus that will start. Now, I am going to introduce what is the analytic function. Analytic function. That is the first topic of your syllabus, complex analysis, your first module. What is the analytic function? Analytic function means, first thing, analyticity. Actually, analyticity is just advanced stage of differentiability. If we take this concept, I have already told what is the differentiability of function. So, advanced stage of the differentiability is the analytic. What is the meaning? Meaning is that I have told you a function is differentiable at point z naught if this limit exists. Means if function is differentiable at point z naught, then we have to say that f dash z0 exists or not. And for analyticity, what is the different here? What is the advanced stage? That is, a function fz is said to be analytic at a point z equal to z naught. At a point z equal to z naught, if fz is differentiable not only at z equal to z naught, but also in the neighborhood of point z equal to z naught. This is the main definition of analytic function at a point. A function is differentiable at a particular point is not only sufficient for analyticity, but function is differentiable at that particular point and also neighborhood of that point. Means this is the basic difference between differentiable function and analytic function. Differentiable function means the derivative exists only at that point. But for analytic function, function is differentiable at that point as well as in the neighborhood of that point. Means that will cover the neighborhood of this point. If this we take this point z naught, so this is the neighborhood, you know that. So now function is differentiable at point z naught and also in some neighborhood. Then we say that function is differentiable at a point z equal to z naught. This is the differentiability. This is the definition of analyticity at a particular point. We can also define this analyticity in our domain. If we take a particular domain, suppose this is our domain, we take a domain, number of points here. If a function is differentiable at most of the points, yeah, you can say if at all the points, if fz is differentiable at all the points of domain D. Maximum points, all the points function is differentiable. Suppose if points we have z1, z2, z3 and so on, if function fz is differentiable at z1, at z2, z3, all the point of domain, then we say that fz is analytic at domain D. This is the different analyticity in a particular domain. If it is differentiable at all the points of the domain, then we say that function is analytic in the domain D. These are the two basic definitions by which you can see, you can understand what is the analytic function and what is the analyticity, right? And now also some other name of the analytic function in some book. It is known as also regular function. In some book, it is also known as holomorphic. These are two other names, regular function or holomorphic function. This is also name of the analytic function. So this is the basic concept. This is the analytic function. Means now, if we calculate all the concepts we have all just discussed, if function is analytic, then it must be differentiable. If function is differentiable, then it must be continuous. If function is continuous, then existence of limit must. Means in reverse order, if we have to check the analyticity, then first we have to check whether limit of function exists or not. Then we have to check if function is continuous or not. Then we have to check function is differentiable or not. Then we discuss about the analyticity of the function. So this is the advanced stage of the analyticity. And now, before starting, what are the methods to which you can check given function is analytic or not? There are some theorems, some necessary and sufficient conditions by which you can check function is analytic or not. Before going to this, first I take up an example, numerical example, how you can check the differentiability of a complex function. If we take an example, example number 1, if fz equal to x cube y minus x upon x6 y square when z is not equal to 0, and this is equal to 0 when z equal to 0, then discuss del df by dz at z equal to 0. Discuss this. df by dz equal to 0 means we have to check differentiability of given function at point z equal to 0. Okay, how we can check differentiability of given function at z equal to 0? By this example, you see how we check the existence of limit of function of two variables and continuity of function of two variables. If we solve this, take solution of this function, here fz is s cube y minus ix upon s to the power 6 y square. If you separate this, open this in real and imaginary part, the real part is s cube y square upon x6 y square minus I times s to the power 4 y upon x6 y square. If you open this into real and imaginary part and compare your original concept, that is we denote the function of complex function, that is u plus iy. So here u is s cube y square upon x6 y square and v is minus x4 y x6 y square. This is real and imaginary part. Now for the differentiability, we have to check the limit at 0. For we have to calculate f dash 0. F dash 0, what is the definition? I told you, if limit z tends to 0, f of z minus f0 upon z. This is the formula of differentiability. So if you substitute this limit z tending to 0, fz means s cube y minus ix upon s6 y square, f0 is given 0 and upon z. This is your definition. Now we check whether this limit exists or not, and I have already told you here every function is a function of two variables, so method of checking of existence of limit is different, and that is we have to check the value of limit is independent of path or not. So for that we further calculate this z tending to 0, and this is s cube y minus ix upon x to the power 6 y square into z. Now we take the limit, we have to calculate the limit along the various paths. As I told you, if we have number of paths, if we take limit first, we take limit z tending to 0 along radius, any radius vector, that is y equal to mx, then what we will get? F dash 0 is equal to limit. Now y equal to, putting y equal to mx, so z converted into x tending to 0, that is s cube m into x, mx minus ix upon x to the power 6 m square x square, z means x plus I mx. We substitute the value of y equal to mx. If you calculate this limit s tending to 0, here x to the power 4 and x, that is total common x to the power 5 m into m minus I. In denominator, here we take common x square and x, that is s cube, then x4 plus m square and 1 plus im. If you this is cancelled out 2, and after substituting value of x tending to 0, finally we get 0. Means limit along this path individually exists. That is the value of 0. This is the limit along first path, y equal to ms. Now again we take this limit another path along path. Now this path is choosing from the given function. Given function is here this fz equal to s cube y minus ix x to the power 6. If you take this denominator and numerator, so here s cube y, here x to the power 6 plus y square, we can take a path y equal to s cube. Then what is the value of limit? This is limit x tending to 0. If we put x cube, put y is again x cube, that is x cube minus ix upon x to power 6 plus x to power 6, that is z means x plus I x cube. Here if you take common in numerator, that is x to power 7, and here x square minus I, and denominator 2x to power 7 1, that is 2x to power 7 1 plus I. x7 is cancelled out. Now we'll put x equal to this, and then we get minus I upon 1 plus I, 2 times, right? This is the value of limit along the path y equal to x cube. This is equal to 0. That means here both limit, this implies that limit z tending to 0 is not independent of path. So limit does not exist, and hence f dash 0 does not exist. In other words, we can say that fz is not differentiable at z equal to 0. Right? This is the method by which we can check the differentiability of the function, complex function at given function. Now, okay, now I'm leaving this topic up to this example in this lecture, and in next lecture, in second lecture, I will continue with this. First, I will take up what are the methods to check the analytic function of given function analytic or not. There are some necessary and sufficient conditions by which we can check any given function to be analytic. Okay, thank you.